Now let's look at about quantum algorithms. First, we will talk about basic concepts of quantum algorithms, like qubit, quantum gates, entanglement, and the tensor product. And secondly, we will talk about quantum algorithms, and we will talk about three algorithms: the Bernstein-Reyzani algorithm, Simon algorithm, Shor algorithm. And Shor algorithm is the most famous quantum algorithms. And now let's first look at qubit. What is a qubit? Qubit is like a bit in traditional computer, and it has 0 qubit and 1 qubit, and this form is a vector notation in physics, and 0 bit is 1 0, 1 bit is 0 1, and if I write a new bit qubit in this form, it can be written as like this. And we know every qubit must be a unit vector. Therefore, alpha square plus beta square is 1. And we can treat alpha square and beta square as the possibility of the qubit phi being measured in qubit 0 and in qubit 1. Like in the coordinate system, this is 0, this is 1, and phi is a vector here. And we measure the qubit phi along these two direction, and the probability of being measured in 0 is alpha square, and the probability of being measured in qubit 1 is beta square. Now let's look at 1.2 quantum gates, and I will introduce some basic quantum gates like X gate, Y gate, Z gate, and H gate. X gate is these gates can be represented in matrices, and X gate is 0 1 1 0. It just make the bit flipped to along this direction. And the Y gate is 0 minus I 0. Z gate is 1 0 0 minus 1. And H gate, we call this a Hartmut gate. It's represented as 1 1 1 minus 1, and we normalize it with square root 2. And X gate has a name of bit, we call it bit flip, and Z gate we call it phase flip. And there's 2 qubit gates. It's control NOT gate. The matrix form is 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. It means that if the first qubit is 0, then we flip the second qubit. If the first qubit is 0, then we do nothing to the second qubit. If the first qubit is 1, we flip the second qubit from 0 to 1, from 1 to 0. And now let's go into the 1.3. It's entanglement. Quantum entanglement is one of the most mysterious part in quantum mechanics. It's like if we have 2 qubits entangled if we measure the one of the qubit, then the other qubit, the state of their other qubit will be determined, will be changed. Like if we write a state like this, if we measure the first qubit, if the first qubit is 0, then the second qubit must be 0. If the first qubit measured as 1, then the second qubit must be 1, and therefore the state of second qubit is changed. And how can we produce such a state? We will use control NOT gate and Hartmann gate. Not Hartmann gate, but some state like this. And plus is just the superposition of 0 and 1. Minus is also a superposition. And therefore we can produce the entanglement state. And let's write the plus and 0, the state here is 0, 0, and 1, 0, right? And we know the control NOT gate makes some bit flipped. The first is 0, the no flip. The first is 1, we got it flipped. Then we get this entanglement state. What's the difference between these two states? If we measure the first qubit, then here, then the second qubit will not be changed. But if we measure it here, obviously the second was determined. Quantum entanglement is also very important in the design of quantum algorithms. And now let's look at the first part of tensor product. It's just a notation like this. We tensor two vectors. It's just like the in the third part, tensor product is the product of tensor product is the whole state of the system. Tensor and we write it like this. And we tensor the two parts, and we get this. And more generally, if I have a matrix like A, B, C, D, B is E, F, G, H. A tensor B is just A, E, F, G, H, B, E, F, G, H, C, E, F, G, H, D, E, F, G, H. We have two by two matrices, and we finally get 4 by 4 matrices, right? And we should notice that a tensor product is the tensor of two states, and entanglement can be written like the tensor of two states. Just like this state can be written as this form, the tensor of these two parts, but for this part we will never write it as the tensor of two parts. Before I enter into the quantum algorithms, I want to introduce the quantum circuits. is the basic parts of quantum algorithm is how the quantum algorithms are processed. And if we have some input qubits here and a function gate like here, and we should notice that the quantum gates, also the function gates must be unitary matrices. Unitary matrices. That means it can have an inverse of the gates, and it means we can restore some states back to the input. So let's look at this quantum circuit. After it, we get our fx, the output, and we inevitably get some junk qubits. But we can't eliminate these junk qubits. We can't take them out. And also, if we do some operations on junk qubits, and it will have some influence on the fx qubits. It's just like the state here is fx tensor junk qubits here, and if we change this one, and the state of the whole system will also change because of the tensor product. And how can we get rid of these junk qubits? As I mentioned before, every quantum gate is unitary matrix. Then we get this inverse, and we get back the input qubits, and we finally get rid of the junk qubits. But we also get rid of the output qubits, fx. And how can we restore the fx? It's just by using the control NOT gate. We introduce some new qubits here to store the information. And we should know that the control NOT is XOR operation, and also a plus operation in the final field F2, final field 2 of order 2. Because we know if the first one is 0, it make no influence on the output. If the first qubit is 1, then got it flipped, and we found this truth table is the same as that of XOR truth table, and also it suffices the plus operation on final field of order 2. Therefore, we can, if the stored qubits here is all 0, then the final state is fx XOR 0. And also, if this is then if it's as they are 0, they will have no influence on the final state. Therefore, this information here is just fx. So this is just the basic components of a quantum circuit, and how we construct such a quantum circuit to process some functions. And so now we can go into the world of quantum algorithms. First, let's talk about Hartman transform. As I said, hard mod the gate is like 1, 1, 1, minus 1 over square root of 2. And if I have many hard mod gate here to form a whole hard mod gate, then what's the product of this hard mod transform gate? If we have some input u, then the final state is just sigma 1 minus 1 over u times y over 2 to the y over 2 y. Y is from 0 to 2 to the n minus 1. Sorry, here is n. N is the number of qubits. And from this we know the hard mod transform distribute the input into the new field, each with the possibility of 1 over 2 to the power n, and normalize it, we just take the square root of it, and we get this. And also, as I have said, every quantum state gate is unitary matrix, and the inverse of H is just H itself. It means H times H is I. Then we add a hard mod gate here, then we will restore, we get U again. Use this, we can develop the Bernstein-Verezani algorithm. This algorithm is used to solve this question, like if we got string U, like some 00100, we have U here, and we also have a function fx is x plus U, and we want to know what U is, and traditionally we input x and get out of fx and try many times, and finally solve a function and solve for U. But quantumly we can do much faster and much with fewer steps, and we construct a hard mod gate with all zero qubit here, and we get, and by this equation, we get the state here is sigma 2 to the n over 2, and x is 0, and 2 to the n minus 1. N is a qubit, the number of qubits. And we also have a function gate here to process this fx, to get the output fx, and also necessarily we have some other qubits to store the output of fx, and this UF contains all this part, and this means here we still get the state like the previous part, and the next we write the quantum state here like this. we know the store gate family is tensor fx. We should know that if the initial state of the store qubits here is phi, then here we write it as fx XOR phi, like as we have talked. And here we write it like this. And if we and in this algorithm we set this phi like minus. Here is fx XOR minus, and we rewrite here like XOR minus. It's like if fx is 0, then the output here is minus. If fx is 1, the state of here is minus qubit. And the proof here is obvious, like minus is square root to 0 plus square root to 1. Minus here. And if the first qubit is 0, and it keeps itself. If the first is 1, we bit flip the second qubit, and the output here is 1, 0. It's just minus qubit, right? And therefore we can rewrite here like this: x tensor minus 1 fx times minus qubit, and we put it here like sigma fx is 0 minus 1 fx 2 to the n over 2 x tensor minus, and also fx is, and fx here is actually x times u, and this part is minus 1 u times x. It's like this: tensor minus 1, and we don't care about this part. And is it familiar? We look at here, this part is Hartmann transform. If it's just equivalent to this part, then equivalent to this part, then and we finally get the output here. And how can we get u? We just use another Hartmann gate here, and we finally get u, right? Then we complete the quantum circuit with Hartmann H. Then we finally get u. It's just directly get u. And sorry, here there is no Hartmann transform over the storation qubit here. And this part we found the quantum algorithm is much more efficient. We just used 3 quantum gates to solve the problem, and it's much faster, and the number of qubits is also exponentially effective. Like with n qubit, we can denote 2 to the n power n number. It's like 0 to 2 to the power n minus 1. And we also, but traditionally we will have 2 to the power n lengths x to solve the problem, and 2 to the power n times to get the final equations to solve the for u. And now let's look at the second quantum algorithm. It's Simon algorithm. In this algorithm, the problem is that we have function fx. It's fx xor some other string L. We know F, and we want to solve for L. We want to know L. And as I said in binary world, the XOR is just a plus operation. Then we can treat it as a periodic function. We solve it like a periodic function. And in this question, we have three steps. First, we set up the quantum state like this: R plus L. It's just like FR is the same as FR plus L, like it's a periodic function. And the state of R and R plus L got some superposition. It exists at the same time with some probability, and in this question with the same probability. And second part, we will introduce the concept of Fourier sampling. We don't need to test many times. We just take a few times to get some samples from the quantum circuit. It's enough to solve the problem. And actually, finally, we need repeat several times to get enough samples to solve the question. And now we build a quantum circuit like this. It's all zero. And we use a Hartmann transform to produce the state here. And similarly, we will have a storage qubit and a function gate. And here, similarly, we get fx and XOR what? We will keep it here and talk about it later. And as I said, it's actually the storage qubit here is also minus. You just put minus here. Then the final state, not final, but the state here is sigma 2 to the n power of 2 x tensor fx xor minus, right? And we really measure the fx here. It's like I said in the entanglement part, we measure some part of the quantum state, then the state of the whole system will change because of entanglement. And we measure here, and we got some output Fa, right? Then the state of the input qubit here is got some changes. After measurement, what happens here? We can reform the state in this part. Actually, like in Bernstein-Verizani algorithm, this part can be represented as like this, right? Then and the state here is just like this, right? And fx here is x plus L. L is the what we want to know. And after we measure the output, we got some FA. Actually, we got two answers here. We said the first is R, the second is R plus L. And the state here become square root of become R plus L. The state we want has already get. And actually we don't. We can also don't use measurement here. Similarly, we use this result to reform the state here, like 1 over square root of minus 1 fx is x plus L. We get the state like 1 over square root of 2 and the sigma minus 1 ry. Here we get the state is y over 2 to the n over 2 and plus 1 over square root of 2 sigma y minus 1 r plus L y. It's just the use of the equations of Hartmann transform. And here we write it like 1 over square root of 2, and we found some same components here, and we take it out like ry minus 1 to the power of ry 2 to the n over 2 sigma y and y, and 1 plus minus 1 to the power of ll, right? It's the same like this, same as this. And we have two cases here. If ly is 0, then minus 1 to the 0 is 1, and it's 2 here. If ly is 1, then here we got 0. Then this state y will disappear, and therefore after when we measure y, when we measure the quantum state, we got y, and y must suffice ly is 0, right? And what we got is y, and we want to know what L is. We just solve some equations to know what L is. Here, as I mentioned before, we use Fourier sampling here. In the basic operation of measurement, we want to we aim at knowing the probability of being in each state, but Fourier sampling is to get some samples from the quantum state, and from these samples we can know what we want to know. And we just get some samples of y, and we use this y to solve L, and we just repeat it sometimes to get enough y. And later we will show the true algorithm in computer on quantum computer to implement such a algorithm. And now let's look at the most exciting part and most hard part. Shor algorithm. As I said before, it's the most famous quantum algorithm ever in the world until now. And what the algorithm want to solve is just the factorization of numbers. It's very useful in cryptography. And we want to introduce some traditional ways to figure out the factors of a number. And for example, we want to know the factors of 21. And we set a function fa is equal to x2 to the power a and mod 21. It's like a finite field. And we just try sometimes when a is 0, the fa is 1, a is 1, fa is 2, and I will directly write some outputs here to find something we want to know. And let's stop here. We found that 1 repeated here, 2 repeated here, and it's actually a periodic function. And fa is actually a periodic function, and the period is 6, right? And what is use of knowing the period? It's just like 2 to the power 2 mod 21 is 1. And for every x, and here we took, I forgot to mention, x is 2 here. For every x, x to the 0 is always 1. And in this particular particular situation, we know 2 to the power 6 mod 21 is 1. And what can we do here is move it here and decompose this part. And we know this is 7, this is 9. We got now we got to number 7 and 9, and the next part we want to know the factors of 21. What we do here is obviously 7 and 9 is not factor of 21, and what we do here is got the greatest common divisor of 7 and 21 is 7. Greatest common divisor of 9 and 21 is 3, right? 3 and 7 are factors of 21. Now we solve the problem. And this is traditionally what we are doing to factorize a number. And we should try many times to find this good period. It's like for x is 2, we found the period is 6. But what if this period is an odd number? Then we can't decompose this part here as this. So we need to try another time, use another x to again solve the problem. And after we try, sometimes we get what we want. And now let me introduce what quantum algorithm do, what Shor algorithm do. And first, for one is quantum Fourier transform. Fourier transform sounds very cool, very difficult, and we write the inverse of quantum Fourier transform. Is quantum Fourier transform has the same form of discrete Fourier transform. It's just like 1, 1, 1, 1, and this is omega, and if we write the indexes of the entries, 0, 1, 2, n minus 1, 0, 1, n minus 1, then at some position ij, the entries is omega to the I times j power. What is omega? Omega is the root, the root of unity. Like x to the n is 1. Omega is root of x. Yes, we consider this equation in complex plane. X is a real number, imaginary number, and we treat it like a rotation along the 0, 0. And if n is 3, we rotate 3 times, and this is omega. This is omega 2. This is 1, omega 2, and then omega is solved like this. And this is the form of quantum Fourier transform. That's very useful for us to find the periods of a function. Like in this part, what I have introduced is after we find the period, we can easily solve the problem. And quantum Fourier transform can help us to find the period. It works like this. We have a periodic function here with period r, and the total length is m. Then after quantum Fourier transform, we got another period function with period m over r. And after we know m over r, m is what we already know. Then we can solve for r, right? So this is just what we will do for the finding period. We solve the problem similar to what we have introduced about Simon algorithm and Bernstein-Verazani algorithm. We build the quantum. First, use a Hartmut gate to generate the state x is 0. This time we have n input qubit, and we denote capital N as 2 to the power n is the number of the figures that n qubit can represent to n minus 1, right? The state here is just this, and we have a quantum function gate. Here is fx. Then the state here, write it like this tensor fx. right? It's x is 0 and minus 1. Sorry, it's n over 2 x fx. And now we will use the quantum Fourier transform here. It's very mysterious. It's very powerful here. We use quantum Fourier transform. Actually, quantum Fourier transform turns some x into the another distribution. It's like this, similar to Hartmann transform, right? This also, we just change the number here, and the omega is just is 1, is nth root of 1. And what I want to emphasize is Hartmann transform is just a special case of Fourier transform of order 2. It's like in the complex plane, this is minus 1, 1. We use 2 times and we get back 1. Right? Minus 1 is just the second root of 1. Why we don't use Hartmann transform here? Because in Simon algorithm, the problem we want to solve is just repeat 2 times for some specific fa. It will only be repeated 2 times along the whole domain, right? You can prove it after this video. It's very easy and just an easy fact. But in this part, we want to find the period, but we don't know the period, how much the period could be. Therefore, we use a more general case, general quantum Fourier transform here. And now we go on with this part. We write this part in the previous equation, and as after quantum Fourier transform, the x actually changes to here. We get x, use x, we get a new y, and we write it like this: 2 to the 1 over y is 0, 2 to the n minus 1 omega x y y fx. Right? For a single x, we get this part, and we take this in, and we get x is 0, 2 to the n minus 1, and we got 2 to the n over 2. Right? We would make it more clear, like this: sigma x is 0 to actually write capital N here for more clear. Minus 1 omega to the power of xy y fx. Right? After the quantum Fourier transform, the state of the input qubits here is just this. And we want to reorder this part, like we know the fx is a periodic function. For fx is some number here. We got many we got many x for the same fx value. So we want to write it like this. We group all these x's with the same fx value, let's assume fx is z. We got y z omega xy. This part denote will group some x here to the same part. The x, for a single z, all the x is the solution of this equation. And as I have mentioned, for a single z value, we got many x0, x1, x2 for this, and we group it together like this, and like this part, and we sum all the y, and we sum all the z, and keep the 2 to the power n here itself. And what we care about is just the constant, the coefficient of each quantum state, because it is related to the probability that we can measure this quantum state. And the coefficient is just like this part. This is the coefficient of this yz state, because this sum is for y, this sum is for z, then we don't care. This just a sum of the state. So the coefficients is this group, the group of these two parts, and the probability is just the square of it. And as I have mentioned, we got many x's for the z, and actually, as I said, fx is also a periodic function of, we say the period is r, then we can denote all the solution of the equation, like the generalized form of the equation is x is x0 plus kr, right? It's the period is r, and k is the index. And we should mention x must be less than n minus 1. Then the range of k is less than n minus 1 minus x over r. Therefore, we can rewrite this number like 2 to the power n, 2 to the power small n, and sigma k is 0. And we know the range of k is this n minus 1 minus x0 r. Actually, k may not be may not take this number, but just the closest number to this n minus 1 minus x0 over r. And omega x is represented as like this form. Y square is 2 to the power 2n, and we break down this part, x0 y square, and sigma k is 0, n minus 1 minus 0 x over r to the omega to the power k ry square, right? This is the probability we can measure. We measure the quantum state like as in yz state. This part with high probability, every element here is close to the real axis, because if it is not close to the real axis, then we're assuming it like omega to the power ry, and we times it. We got here with time, multiply, and indeed we got some offsets here, right? Many part offsets, but if it's close to the real axis, we got some multiply. It's just the whole rotate. Like even here, if ry is close to some if it's close to some integer, it got some whole rotation. And to make it more clear, we write omega like e to 2 pi I over n, right? It's a simple, and the omega to the k ry is e to the 2 pi I k ry n. Actually, if this part is close to some integer, then this part will always close to some. It will be like this. We rotate it. We rotate it. It's almost like rotated 2 pi degrees. It's a whole rotation, right? Then with all of them is 1. The probability to be measured in this state will be higher. Thus, we know ry over n must close to some integer c. And after measurement, we know some y, and n is also what we know. It is 2 to the power n. And we rewrite the equation like this. This is the number we know, and we want to solve this. Actually, it is a total mathematical problem here. And then to find the closest c over r to this part. For example, if the n is 8, we got y is 3. We got many fractions to approximate this part, this 3/8, like 5 over 2, 2 over 4, 1 over 3. They are all approximations, but there is one that is closest to 3/8, and we take this, and we got some possible r. And actually, we don't know whether this r is appropriate. Is just what we want, and we try another time. We get another y, and we got another fraction here, and we approximate another time, and finally we get some r, some very possibly, and we tested this r in this procedure. We test if this R is good enough to help us find the answer of the solution. And if it is not good, we just try another time. And without about 3 times, we can get a very high probability to solve the factorization problem. Finally, let's have a recap. And in this video, first we talk about the concepts of in quantum computing, and we introduce 3 important algorithms, and with each of the algorithm is exponentially advancement compared to traditional algorithms. And we also show the algorithms in detail, the mathematical form of each algorithm, although they are seemingly difficult. And finally, I want to talk about something very not irrelevant to this topic. It's like some new algorithms. It's quantum annealing algorithms. Like in machine learning, in AI, we want to find the global minimum of a function, or a good local minimum of a function. And if the function is like this, it's hard to get out of this, to get the better minimum, right? Like graded descent, we just be stuck here. We're just stuck here and can't go to here to get a better local minimum. And annealing algorithm, traditional annealing algorithm use the thermodynamical principle to make the function, make this function to find the better minimum. And even in traditional annealing algorithm, we still have to jump over this still gap. Annealing algorithm just help us to jump this gap. But if we have some, in quantum annealing algorithm, we have quantum kernel effect. It's like we can quantum kernel, we can directly jump through the function into this part and get the minimum, a better minimum. But actually, we haven't built such a quantum computer to implement the algorithm. And I want to talk about the principle of measurement, how we measure the qubit. Like I have said, this CNOT gate can use to produce entanglement state. Even more generally, it's alpha, beta here, and we use more and more control NOT gate to generate a longer and longer quantum entanglement state, and even to the 30 or 40 qubits. But actually, in macroscopic world, we have no quantum entanglement state. We can observe no quantum quantum entanglement. We observe no entanglement state in macroscopic world, right? And this means this entanglement state cannot hold. It just collapses into some zero state or one state. But as we have talked about, it is the collapsion has some probability to be collapsed into these two states, and the probability is just alpha square and beta square, and this we know the probability, and this is just the principle of the measurement. And thank you for watching this video. I think it's a long video,